topic is expected value. Here's that definition. Expected value is a mathematical way to use probabilities to determine what to expect on the average in various situations over the long run. So expected value is a way to calculate an average when probabilities are in play. And one place where this happens is in games, and in particular gambling games. And those are the kinds of examples that I'm going to do in this video, because that's where I've used expected value in real life, is in gambling scenarios. But you can also use this in much more mundane scenarios, like when you're buying insurance or something like that. There's an expected value in play there. So I'm going to do the gambling kind of examples in this video, and then we'll do that more boring stuff in the next video. Before we can do any examples, we need to know how we're going to figure out an expected value. And here's our rule. To compute an expected value, we multiply each possible outcome by its probability and then add these products. So what we do is we figure out all of the things that can happen in the experiment, all of the possible outcomes, and we figure out how likely each of those are, so we find their probabilities. And we weight each possible outcome by its probability. So the more likely something is, the more weight it will have in the expected value. And then we just add all of those products together, and that's what we call the expected value. And again, that expected value is like an average over the long run. Here's a simple example. You play a game where a fair coin is flipped. Heads and tails are equally likely. If the coin comes up heads, you win $1. If the coin comes up tails, you lose $3. Find the expected value of your profit over the long run. Now, your intuition's probably telling you that this is not a fair game for you. Because heads and tails are equally likely and you lose more money than you win, then you're expecting negative profit over the long run. That is, you should expect to lose money. Well, we're going to use math to figure that out. And not only are we going to figure out that you expect to lose money, but we're going to figure out how much money you expect to lose on the average. Now, I think we can use our intuition to figure this out. If we play this game twice, we would expect to win once and lose once. That's not necessarily what would happen, but if the coin comes up heads half the time and tails half the time, then the expectation is that we would win once and we would lose once. So we'd win $1 and we'd lose $3 for a net loss of $2. But that was over 2 games, and so we've lost $1 per game. So intuition tells us that our expected value should be about $1 lost per play. Let's see what the math tells us. To compute an expected value, we multiply each possible outcome by its probability and then add these products together. So one of the possible outcomes is that you win $1, and I'm going to represent that by a positive 1. I multiply that by its probability. The probability I want here is the probability that the coin comes up heads. Well, that's 1/2 because the coin is fair. So this number right here is the probability that the coin comes up heads, and we multiply it by the outcome when we get heads on the coin, which is a win of $1. Then we find the other possible outcome, which is that we lose $3. I'm going to denote that by -3, and I'll show you why I want these parentheses here in a moment. And I multiply that by its probability. Well, that's the probability that the coin comes up tails, which is also 1/2, again, because the coin is fair. Then the formula says we're going to add these products together, and that's why I put these parentheses around the -3s, just so I didn't have a plus sign next to a minus sign, because we math people think that looks funny. It just looks prettier with those parentheses there. We'll follow the order of operations. We're going to multiply here first, 1/2. Then we multiply here, -3/2. When you multiply an integer by a fraction, you only multiply the numerator by that because you're thinking of this as being over 1. And then we add those two things together. We already have a common denominator, so adding straight across in the numerator, I get -2 divided by 2. And there's that -1 that we predicted. This is an average loss of $1 per play. Now, if you look at the scenario, you can't actually lose $1 when you play this game. You either win $1 or you lose $3, but this is the average lost per play. If you were to play this game many, many times, you'd expect to lose $1 per play. So if you sat there and played this game 100 times, your expectation would be to lose $100. If you only played this game once, you might win, and then you should quit because you're ahead. The expected value tells us that over the long run, if you were to sit and do this for a long time, eventually you're going to wind up losing. Unless you cheat somehow, you're going to lose. Now, this is a good way to organize our work, but I've got something that I think will look a little better and keep your thoughts a little sharper. I'm going to encourage you to make a table. So on the next page, I've made a table of the outcomes. So in the X column, I've got the two possible outcomes, 1 and -3. You can win $1, you can lose $3. And then next to those, I've put the probabilities, 1/2 and 1/2. This is the probability that the coin comes up heads. This is the probability that the coin comes up tails. Notice that that column adds up to 1. That guarantees that we've covered all of the possible outcomes. Now what I'm going to do is make a third column in that table where I multiply straight across. So I take each x times its probability. So 1 times 1/2 is 1/2, and -3 times 1/2 is -3/2. Same numbers we got before. And then I just add down this column. 1/2 plus -3/2 is -2/2, which is -1. And so our expected value is -1. The notation that we often use for expected value is E. If you've played any gambling games before, in particular if you've played poker, you may have heard this called the EV for expected value. That's exactly what they're talking about. Your EV is just your expected value in a gambling scenario. Let's try another one, and let's do a poker example. A poker player is trying to determine whether or not to call a $40 bet. So to call a bet means that somebody else has bet $40 and you're going to bet $40 as well to see the next card come out or to flip hands and to see who won. If she calls and wins, she'll profit $250. If she calls and loses, she'll lose the $40 that she bet when she makes the call. The probability that she wins is 20%. Find her expected value. And then using that expected value, we'll answer the question, should she call the bet? Would it be a winning play in the long run to call that bet? Let's use this table idea to organize our thoughts. So there are two possibilities. She'll either profit $250. Let me put this in another color so it'll stand out. So she could win $250, or she could lose $40. We want to represent that loss by a negative number, -40. That's her profit. When profit is negative, it means you lose money. The probability that she wins is 20%. So I'm going to use the decimal version of that, which is 0.2. We could also convert that to a fraction and use 1/5. You don't want to put the 20 in there because that's not a probability. That's a percentage that you need to convert to a decimal. And then it says find her expected value. It seems like something's missing. We're missing a number in the table. But remember, this column has to add up to 1. Or going back to the problem, if the probability that she wins is 20%, then the probability that she loses will be 80%. And so we're going to put a 0.8 right there for 80%. Notice that this column now adds up to 1. Now we multiply each outcome by its corresponding probability. This weights each outcome by how likely it is. So it takes into account not only how big or small the outcome is, but also how likely it is. And this is how we get an average. So we take 250 times 0.2, that's 50. And we take -40 times 0.8, that's -32. And then we add these together to get the expected value. And the expected value is 18. That's $18. Now, she can't actually win $18. That's the average amount that she'd expect to win over the long run per play. The more times she makes this bet, the more likely she is to win over the long run. She might get unlucky the first few times and lose. In fact, it wouldn't be unlucky for her to lose. She only wins 20% of the time. But she wins so much more money than she loses that over the long run, this would be a winning play. So she should call the bet. Calling the bet over the long run would be a winning play. Even though she expects to lose more often than she wins, a lot of times this seems counterintuitive to people. There's something in people's intuition that makes them think that if you're going to lose more often than you win, then you shouldn't play. That's not true, and I can give you a simple scenario. We're going to play a game where I'm thinking of a number between 1 and 10. A whole number. I'm not going to trick you and be a dork and say, haha, it was pi or something stupid like that. I'm going to pick a whole number between 1 and 10 inclusive. You're going to pay me $1 and then guess. And I'm not going to cheat. If you don't get my number right, I'm going to keep your dollar. But if you guess it right, I'm going to give you $1 million. Now you're going to lose that game 90% of the time, right? There are 10 different numbers to pick from. I'm picking one of them at random. That means you've only got a 10% chance of winning. So you're going to lose most of the time. But when you win $1 million. You'd be an idiot not to play that game. Even though you're going to lose it most of the time, eventually when you win so much money that it becomes a winning play. That's the same idea here, it's just not as extreme. Over the long run, she expects to win $18 per play. So if this is like a professional poker player, and she plays poker all the time, and she winds up in this situation 1,000 times in her poker career, that's $18,000 that she can pretty much count on in the long run. Now, for you real poker players, I know there are other things involved, like whether or not she's playing in a tournament, or how much money she has behind it, and stuff like that. Don't take any of that into account. This is just the raw numbers. From the perspective of the math, taking all psychology out of play, she should call the bet. One more example, and this is one from the craps table. So if you're not familiar with the game of craps, somebody, they call him the shooter, rolls 2 dice, and then there are all kinds of bets that you can make. The main bet is the pass line or the don't pass line. And that's the game where you have to roll a 7 or 11 on the first roll and you get a point or whatever. But there are all these side bets that you can make on each individual roll. And one of them is called the field. And so what we're going to talk about is making a $5 field bet. $5 is usually the minimum bet, and I'm just a lowly math instructor, so that's all I can afford. So here's how it works on a $5 field bet. The shooter rolls the dice, and they add up the number of pips on the top. And if that adds up to 2 or 12, then you profit $10. So you actually triple your money. If you put down a red $5 chip, they're going to put 2 red chips right next to it, and you're going to rake them back. So you're going to bring back $15, but remember, you bet 5 of it. So your profit is $10. You win triple the amount that you bet. So your profit is double the amount that you bet. If a 3, 4, 9, 10, or 11 is rolled, you win $5. So you win the amount that you bet. You essentially double your money. So your profit is $5. The quote only unquote ways that you can lose is if a 5, 6, 7, or 8 is rolled. The house takes those 4 numbers, and if you put a red $5 chip on the table and a 5, 6, 7, or 8 is rolled, then the house just takes your money, so you lose $5. So at first glance, this is really enticing because we win on 1, 2, 3, 4, 5, 6, 7 numbers, and we even win twice as much on these most extreme cases, snake eyes and boxcars. And we only lose on 4 numbers. It looks like a really good play. But if you have any idea of how the casino industry works, you can probably guess where this is going to go. We'll do the math anyway. Find the expected value of a $5 field bet. And then, as a follow-up question, if you made this bet 1,000 times, what is your expected profit? How much money would you expect to win or lose in the long run? That's a long run right there, 1,000 trials. You would expect your winnings to come out pretty close to the expected value over that many trials. On the next slide, I've organized our table, and I've got the dice off to the side for reference. This is the sample space that we used for the 2 dice example a couple of videos ago. Let's go back to the scenarios. One possibility is that you profit $10. We'll represent that by positive 10. A second possibility is that you win $5. We'll represent that by positive 5. And then the sad scenario is when we lose. We lose our $5. So those are the 3 different outcomes here. This is a little bit different than the previous 2 examples because there are 3 different things that can happen. We can win $10, we can win $5, we can lose $5. We want to make sure that all of those scenarios are listed. Now we have to come up with the probabilities. We profit $10 when a 2 or a 12 is rolled. Well, there's only one way to roll a 2, and there's only one way to roll a 12. So that's 2 possibilities out of the total of 36. Remember, there are 36 ways the dice can come up because there are 6 rows and there are 6 columns, and 6 times 6 is 36. So that's 2 36ths. I know that fraction reduces, but I'm not going to reduce because remember, eventually I want to do an addition step, and if I don't reduce, I'm guaranteed to have common denominators. Let me erase these, and we'll go back to the explanation of how a field bet works. If a 3, 4, 9, 10, or 11 is rolled, you win $5. Let's see. 3, 4, 9 is here, 10, 11. Feel free to pause the video and make sure that I didn't miss anything. But those are all the different ways that you can roll a 3, a 4, a 9, a 10, or an 11. Let's count them up. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That might have been a weird way to count those. Let me go down the columns and just show you that I didn't miscount. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 ways that we can win $5. And there are 36 total possibilities. So 14 out of 36, which again reduces. I'm not going to reduce because it's going to guarantee that I have a common denominator when I get to my addition step. Now the truth is starting to come to light. That's only 16 possibilities. There are 36 total ways the dice can come up. So when they say that we lose on a 5, 6, 7, or 8, and that's only 4 of the possible numbers, well, those are the most common numbers. Those are the ones in the middle here. We can figure out how many there are by simply subtracting from 36. There are 36 total possibilities. Here are all of the winning ones. So that's 16 possibilities that we can win on. There are 36 total ways the dice can come up. So that's 20 ways that we can lose. But if you're not convinced, we can just count them off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 losers. So we lose more often than we win. That doesn't guarantee that we're going to lose money, though. We saw that in the last example. Maybe the fact that they double us up in this scenario means that we'll actually win money in the long run. And of course, we don't really believe that because this is a casino bet. They'd never let us win over the long run. There are very few long run winning plays in the casino. So we multiply each outcome by its corresponding probability. We're multiplying integers by fractions, so we're only multiplying the numerator. Think of this like it's 10 over 1. So 10 times 2 36 is 20 36ths. 5 times 14 36 is 70 36ths. And here's where we get the bad news. Negative 5 times 20 is negative 100. And now we can see that this is going to add up to a negative number. If I add down this column, I get an expected value of negative 10 over 36. And I don't know what that is off the top of my head. So let's put this into the calculator. I'm going to ignore the negative and just do 10 divided by 36. I want the decimal, not the reduced fraction, because we're talking about money. And in our system, we put our money into decimals. We don't really talk about fractions of money I mean, that's not always true. We do say a quarter, but most of the time we use decimals. That's a 0.28-ish if we round to the nearest cent. Remember, ours was negative. So this is negative 0.28. What does that mean? That's a loss, because it's negative, of 28 cents per play. That's 28 hundredths of a dollar. So that's 28 cents per play. Once again, you can't actually lose 28 cents when you play this game. This is an average loss. Over the long run, you would expect to lose 28 cents per play. Because that's such a weird number, I asked this follow-up question. If you made this bet 1,000 times, what is your expected profit? Well, over 1,000 plays, we expect to profit, well, let's see, our profit per play is negative 28 cents, and we're making 1,000 plays, so we would multiply that by 1,000. Multiplying a decimal by 1,000 moves the decimal point 3 places to the right. So that's negative 280. That's a loss of $280. This time it's not per play, that's a total, because we're talking about over 1,000 plays. So if you were thinking that it would be a good time one day to go to a casino, maybe go to the boat, and go play craps all night, and you're going to bet the exact same amount bet on the field all night long, I've got a better idea for you. You should just go to the top of the boat and chuck your chips into the river one at a time, because you won't waste all your time standing at the dice table, and you can go enjoy the buffet way earlier. Making this bet over the long run is not a good idea. The only way you can win on the field bet is to vary the size of your bet and get lucky when you bet big and lose when you bet small, or to cheat, somehow cheat the casino.